Hello, I'm Alvarez, and I'm going to be telling you all about this work on improving Subgraph-GNNs via edge-level ego network encodings. This is joint work with Andreas Kaltenbrunner and Vicenç Gómez. Let's dive in. Before we start, some preliminaries. Graph neural networks, and specifically MP-GNNs, have become widely successful in recent years. Their expressivity has been analyzed through the lens of the graph isomorphism detection problem, in which we are trying to detect whether two graphs are isomorphic or not. Now, if two graphs are non-isomorphic, but their graph representations are the same, we'll say that a given representation is unable to distinguish them. Interestingly, it has been shown that MP-GNNs are at most as powerful as the one-dimensional Westphal-Riemann test, or 1WL. Due to these limitations, recent research has focused on improving the expressivity of MP-GNNs. Some approaches do so by introducing additional expensive preprocessing or more complex message passing, with implications for their scalability. Some popular approaches, like Subgraph-GNNs, consider, for instance, the subgraph surrounding each node, edge, or some subgraph sampling policy, which have been shown to be at most as expressive as 3WL. 3WL is a variant of 1WL that is more expressive and that has higher distinguishing power. In this work, we ask ourselves, what does it take to actually distinguish those 3WL equivalent graphs on a budget? Before we try to answer this question, we have to first introduce a family of graphs that are 3WL equivalent. And in particular, in this work, we're going to be heavily focusing on strongly regular graphs. We say that a graph is D-regular if it has n nodes, and each of the n nodes has D neighbors. That is, the degree of all nodes is D. Additionally, we say that a graph is strongly regular if there exist two parameters, lambda and mu, such that every pair of adjacent nodes has lambda neighbors in common, and every pair of non-adjacent nodes has mu neighbors in common. In these two graphs that we are showing in the slide, we see the Srikande and 4x4 root graphs, which are 3WL equivalent strongly regular graphs with equal parameters. With the introduction out of the way, let's jump right in. In this work, we propose LN, an edge-level ego network encoding, to improve the expressivity of GNNs by considering edge-level information. LN represents a node by capturing edge distance information in its ego network. Let's break that down. For a given vertex V, we are going to represent it given its ego network at depth k. We are going to look at every neighbor U within that k depth ego network, and then we are going to represent this node V based on its distance to V, the degree of this neighbor, and also the number of edges from U that are one hop closer to V, since V is the root of the ego network, and the number of edges that are one hop further away from V in this ego network. Let's trace through an example. Consider the graph on the left, which is the ego network subgraph of the green node with degree 3 that has a dotted circle around it. What we're going to do is represent the node at the center with degree 4 in blue, which has a dashed circle around it. And what we want to do is, in particular, represent the relative degrees, as we call them, of Ln in the subgraph. First, we consider the position. The blue node is at distance 1. We look at its edges, and there's one edge that's one hop closer to the ego network root in green. So the count for that variable will be 1. Then we look at the actual degree of the node, which is 4. And then finally we look at the number of edges that are going farther away from the root. In this case, we have 2 red edges that are 2 hops away from the root. With that, we have our representation. The previous formulation computes Ln encodings at the node level. However, we also propose a method to compute Ln representations at the edge level. To do so, consider an edge, for instance the edge between nodes u and v. To compute the encodings at the edge level, what we are going to do is compute the intersection between the Ego network subgraphs of u and v. So that looks as follows. First, we start with the Ego network subgraph of v. That's the graph on the left. Then we consider the Ego network subgraph of u, which is the graph in the center, colored in purple. Finally, we compute the intersection of the two subgraphs, which is merely the intersection between the sets of nodes that appear in both graphs. In this Ego network intersection, we have a different distance function to the root edge. For instance, we have node W1, which is at distance 1 from the root, since both U and V require exactly one hop to get to W1, while the red nodes require exactly one or two hops. The choice of whether we represent LN encodings at the node level or at the edge level has implications for expressivity. The last pending item is to describe how we can use those LN signals. In a simple manner, they can be used as sparse feature vectors or as part of message passing formats. However, another approach is to actually learn an embedding for each LN signal as distance or relative degrees. In this work, we evaluate both approaches and compare the empirical performance and expressivity of both of them. Let's now break down some of our theoretical results, for which you can find the demonstrations in the paper. We find that introducing edge-level information through LN has implications for expressivity. Node-level LN encodings are strictly more expressive than other Ego network representations like Eagle and can distinguish strongly rural graphs with different parameters. Edge-level LN encodings can additionally distinguish challenging strongly rural graphs with equal parameters that 3WL cannot distinguish. Furthermore, we show that LNL with the sum as its pooling operator is at least as expressive as raw LN encodings, meaning that the learnable variants of LN are as expressive as the sparse vector variants. And finally, we connect the learnable variants with shortest path neural networks and show that learnable LN is strictly more expressive than SPNNs. Let's look at a proof sketch of why edge-level information is more expressive than node-level information. Here we're showing the Srikandi and 4x4 root graphs that we saw at the beginning of the presentation. And to the right of each of the graphs, we have one hop subgraphs computed at the node level and at the edge level from the node with label 1 and the edges labeled 1 and 2 respectively. If we look at the node level subgraphs, we can see that they are indistinguishable because the degrees, or rather the frequencies of the edges going at every distance from the Ego network root in purple end up being the same. We have 6 green edges and 6 orange edges. Now let's focus on the edge levels of graphs. And here what we can see is that the linking behavior between the two graphs is actually different. So if we look from the point of view of the edge from 1 to 2, there's a different frequency of triangles, there's a different frequency of edges that are exactly at distance 1 versus edges that are exactly at distance 2. And in particular, this means that we can tell apart the graph on the left and the graph on the right, which means that edge level information can distinguish between both subgraphs, while node level information can't. Beyond our theoretical analysis, we evaluate LN on 4 empirical benchmarks to assess its performance. Expressivity, in which we look at isomorphisms, graph property prediction, and counting graph structures. Aid proximity, in which we seek to learn long-distance dependencies, real-world graphs. And finally, memory scalability, in which we evaluate the memory consumption when training on large artificial graphs. On expressivity, we find that LN can distinguish all graphs in the exp dataset, which are known to be 1WL equivalent, and furthermore, LN at the edge level can distinguish all graphs in the challenging strongly regular 25 dataset, which contains graphs that are 3WL equivalent. Furthermore, in the graph properties dataset, we find that LN can boost the performance of both a gene and a GNS kernel significantly beyond previous results. We also report some results on the content substructure datasets in the paper, where we find that LN is comparable to previous baselines. On real-world graphs, we also find positive results. The sparse vector variant of gene plus LN matches Subgraph-GNNs in 2 out of 5 tasks and reaches 99.9% of the accuracy of gene AK in pattern at 18 times lower memory costs. The learnable variant, computed at the node level, is comparable or better than state-of-the-art Subgraph-GNN models with 1.4 to 3.4 times lower memory costs. Finally, the edge-level variant does not produce statistically significant improvements over the node-level variant, which indicates that at least in these practical datasets, it seems that edge-level information, despite boosting expressivity, does not actually improve empirical performance. And finally, we also evaluate the memory scalability of LN as a learnable method at the node level and at the edge level. Here we find that LN at the node level always outperforms the GNNs kernel baselines in all the settings and for all ego network depths. Furthermore, we find that LN at the edge level always consumes extra memory, which is to be expected. Our results confirm that node-level learnable LN is a strong baseline for learning structural attributes from ego networks that introduce edge-level information. Furthermore, we validate that the edge-level variant, although it increases expressivity, it also introduces additional costs. We summarize our main results as follows. LN signals provide a trade-off between computational costs, expressivity, and learning capacity. Gene plus learnable edge-level LN can distinguish all graphs in the challenging, strongly regular 25 dataset. Gene plus learnable node-level LN consistently matches or outperforms state-of-the-art models on structural tasks, edge proximity tasks, and real-world datasets with a lower memory footprint. Finally, Gene plus the sparse vector version of LN encodings are sufficient to boost performance beyond Eagle on Sync 12K and pattern, with up to 18 times lower memory cost than reported for strong baselines such as GNNs kernel. We hope that you found our work interesting. If you have any questions, comments, or clarifications that you would need to be made on our work, feel free to reach to any of the authors. Thank you for watching.